Hi, everyone. It's a pleasure to welcome Ruisheng Diao from Pacific Northwest National Lab. Ruisheng received his bachelor's and master's degrees in electrical engineering from Zhejiang University in China, and then a PhD in electrical engineering from Arizona State. In 2009, he joined PNNL as a power system research engineer. In addition to publishing in the power systems literature, Dr. Diao has a portfolio of research projects in the areas of power system modeling, dynamic simulation, online security assessment and control, dynamic state estimation, integration of renewables, and high-performance computing implementations in power grid simulations. Dr. Diao is a registered professional engineer in Washington State and a senior member of the IEEE. So thank you very much for coming to speak with us.
Again, thank you for inviting me to give this exciting talk here. And I'm Ruisheng Diao from PNNL. So actually, for those of you who do not know PNNL, so we are a national lab, a contractor to the Department of Energy. And we do find solutions to existing and new problems identified in the power grid. So this is one of the projects we have been working on for the past few years on large-scale, high-performance power grid dynamic simulation. And we have a very strong project team consisting of both exciting and engineers from power grid side as well as high-performance computer science side. Okay. So for the past few years, we do see an increase in complexity in our power grid models, especially when we consider the emerging technologies like wind, solar, the increasing amount of renewable energy into the power grid, as well as the demand response activities. How do we better model the power grid, plan the power grid, and further operate the power grid in a secure way that is very critical to the secure operation and of our power grid, right? And then if you see the figure right here, this is about a summary about the Western electricity grid. So the blue bar is the number of buses being used in the models. And back in 2003, it has around 14,000 buses with less than 3,000 generators, right? And then if we look at what's going to happen in 2022, we'll have more than 22,000 buses with around 5,000 generators being modeled in the power grid. And then if we consider all the complicated models in the grid for dynamic simulations, dynamic simulation is a way to simulate and mimic the dynamic trajectory whenever the system is subject to any disturbances. Like, what if you lose a line? What if you lose a generator grid? Can your power grid survive in case of such events, right? And then using today's computer and major commercial software tools, it is very time-consuming to finish one single dynamic simulation. If I download one of the big Western interconnection model from their website and launch one dynamic simulation, in order to achieve the 20-second trajectory, it will take around 100 seconds using my laptop, right? And then this is the simulation time without saving any information to hard drive. If we want to save every single timestamp for all the buses in the power grid, then this 100 seconds will easily grow to 400, 500 seconds, right? So technically, it is several times slower than real time to compute all the dynamic trajectories of a power grid. And then why this is so slow and it's not increasing? That is because the majority of today's commercial software tools were developed around 30 or 40 years ago, right? And then back then, there were no affordable parallel computers back then. It was either too expensive or the algorithm were not ready to be utilized, right? This applied to the traditional power grid, power flow analysis, dynamic simulation, small signal stability, as well as OPF, means optimal power flow solutions. However, the CPU clock speed is not ever increasing because of the physical constraint, which is the heat, right? And then one popular way of speeding up today's computation is to allocate different processors to run different contingencies. Contingencies means scenarios. What if you lose a line? And in a power grid, there are thousands of lines. And if you combine n-2, n-3 contingencies, and then the total number of scenarios will grow exponentially. Right? So one of the popular way in today's commercial software is to do the distributed computing. Right? For example, by using the serial computing using one core, if I want to finish 4 jobs, right, then the total time will be right here. What if we use 4 different processors to launch all the 4 jobs simultaneously, right? And then for some of the cases, given different complexity, and it might take a longer time to solve because of the complicated controller actions, as well as more iterations, right? Then we will have a bottleneck right here. The longest, most time-consuming contingency will always be my bottleneck. This will affect the total computation time, especially if I want to move all the offline planning studies into an online real-time environment. This will be my bottleneck, right? For big models like Western or Eastern interconnection, it will be several times slower than real-time. Then power grid operators might not have enough time to take proper and timely control actions when something urgent happens, right? So let me show you a couple examples. Because distributed computing, if we use different cores to run different contingencies, this is easier to implement, right? The idea here is to use a global task counter just to dynamically allocate cases to different processors. In some of the vendors' tools, this is done in a static way, which is not very efficient. So we improve this algorithm by dynamically allocate processors, not to waste any idle processors. Right? So we test this computational scheme using one of the WCC, means Western Interconnection Coordinating Council base case. And then if we want to run 400 contingencies, and we develop our own C++ code, and then as you can see, the more cores you use, the more speed up you will gain. Right? And this is one simple example. What if I do something crazy by fully leveraging P&L's supercomputer? And by the way, we have a big parallel computer with more than 23,000 cores. Right? So for the same case, and the N-1 means when you lose one contingency and then see the system response, that is one scenario. Right? And then if we run 20,000 cases using one core, it will take around 40 minutes. Right? And then if we use 512 cores, the computation time can be significantly reduced to 4.8 seconds. What if we try 1 million cases? And by the way, this is only a partial set of the full N-2 contingency scan for the big network. Right? Using one core, it will be 68, 69 hours. Right? And then if we use more than 10,000 cores, the computation time will be reduced to only 25 seconds. And then if you look at the scalability, when we have around more than 10,000 cores, we got 9,871 times speed up, which is pretty good and close to linear scalability. Right? And again, this test is done for steady state power flow type of contingency analysis. What if we try the similar concept and apply to dynamic simulations, right? And then in this testing, we launched 160 dynamic runs in the GE PSLF, which is commercial software tools developed by GE. And then same model, but we are now running dynamics. And this model comes with 17,000 buses and 3,000 generators. If we want to run 30-second simulation per scenario, let's look at the time. Using one core, the total time is 535 minutes, right? And then if you're using 80 cores, then the computation time is reduced to 15 minutes only, right? Now, we see a bottleneck, right? But we can only limit ourselves to this if we want to run 16 contingencies using 16 cores. In today's commercial tools, there's no way to further narrow down the speed because you have to do a lot more modifications to the software code in order to achieve better speed up. So here is our research concept. We want to fully leverage today's parallel computer with more and more cores, and to enable the second level of parallelization by using more cores to speed up one single dynamic run. This is one of the major focus of our research inside this project. Right? So as you can see, typically, when you have distributed computing with commercial software tools, you can get to here only, right? But by enabling the second level parallelization, you can have better speed up. Any questions so far? No? Okay. So in order to do this, it's not very easy because you have to fully understand the details of dynamic simulations to access the transient stability problem of a power grid model. Right? So we basically develop new approaches in order to achieve speed up by leveraging today's best parallelization algorithm, including the mass library that's running on parallel computers. And then another key fact is that the cost of HPC hardware is decreasing a lot. Right? About 10 years ago, PNL purchased one machine with like 128 processors. That cost about $500,000. But today, if you purchase the same but better hardware configuration, the cost is only like $50K. Right? So we want to develop the innovative approaches to speed up one single dynamic run, and then we have to integrate the innovative algorithm with commercial software tools. Right? And then regarding parallelization, we need to parallelize the computation of dynamic states. We want to parallelize the matrix computation. Also, we need to find good linear solvers. Basically, we want to solve AX equals to B problem in a much faster way. Right? Also, we explore different HPC platforms. OpenMP is one type, shared memory platform. And another type is called MPI, message passing interface. Right? This is a distributed memory platform. Both have their own pros and cons, right? But we did investigate both of them. And then if we look at Anderson and Forward's Power System Stability book, and if you get a chance to look at that, it has a nice detailed procedure showing you how to run and design a traditional dynamic simulation process, right? So in this testing, we consider classical generators. Basically, one generator has only two state variables describing their DXDT calculation, right? Then we are using constant impedance load model, and then we are using a reduced adaptivity matrix, right, to handling the network coupling side. And then for time integration, we are using the modified Euler method. And then this whole concept was implemented in the OpenMP shared memory platform. And you can see the speed up performance for one single dynamic run. For a case with 1,000 buses and 288 generators, as you can see, the speed up stopped around 4 processors because of the overhead, right? And the size of this problem is just too small. If you use one single thread, the total time to complete this computation is like 3.2 seconds. And then if we use 4 processors, it's just reduced by 1 point something second, right? So I'm not going to invest my money to buy a HPC hardware for a small problem like this because it's expensive and the speed up is not significant. The only problem HPC algorithm can shine is for large-scale complicated models, right? If we look at this WECC model, right, and then we want to run 30-second simulation with 5 millisecond time step, as you can see, the scalability is pretty good. If you look at the green curve, this is the total computation time, including everything, right? So using one course, it can take 232 seconds to complete, and then using 64 cores, the computation time is reduced to 9 seconds. And I want to emphasize that In Anderson and Forward's stability book, the computation process is slightly different compared to what's going on in today's major commercial software tools. Mostly rests with network computation. Then the next thing we did is how do we move the innovative parallel algorithm into commercial softwares. So we did partner with Partech Labs, a software company located in Vancouver, BC. Right? So basically, they provide their APIs, application program interface, for us to call and test our parallel algorithm. Right? And then the APIs they develop include initial state calculation, and also the mapping between the generators and buses, and also the generator equivalent Norton impedance. And that's where you add those impedance into the network admittance matrix for network solution. Okay. And then parallelization rests with the following: the calculation of current rejection, the calculation and update of the state variables of all the generator states. Right? And then for linear solver, we test more than 20 types of available solvers that we could find and identify the best solvers. So these are just a couple examples, including KLU, SuperLU, KSP, and others. Right? And then for iterative solver, we have GMRS plus ISU, and Big Step plus ISU. And this is the validation result. So after we speed up the performance, we don't want to sacrifice the simulation accuracy, right? So that's why we did a comparison by running the commercial software. This is the subset of the DSA tool. This is commercial code, right? And the red curve is the one with parallel implementation by calling the TSAT APIs. As you can see, the two curves overlap each other perfectly, right? And then let's look at the speed up performance. To run a 20-second simulation with 5 millisecond time step, and this model has 2,600 plus synchronous generators being modeled. Right? And then we have two curves shown here. The green curve is the one to complete the computation only without saving anything to hard drives. Right? And then the red curve is the one, say if I want to save the time domain trajectories of all the buses, then I have to save everything inside into the hard drive for post-processing or something like that, right? And then you can see the speed up is pretty good. After around 6 to 7 processors, the scalability kind of flattened out because we have to make a balance between execution of a task versus the overhead time required to communicate between different processors to pass information back and forth. Right? And this table shows a detailed breakdown of where the speed up comes from. Listed here, T minus 0 means all the preparation work before the time integration starts. Right? This includes the power flow solution, including building the network admittance matrices, right? And calculating and updating all the Norton impedances from the generators and potentially loads. Right? And then this one is one column showing the significant speed up. This will include the current rejection calculation, update states, and their derivatives, because naturally different generators do not talk to each other. The only interface between a generator model and the network is through its stator, right? And then between two generators, normally there's no information passing between them, right? And then the next speed up comes from saving the information to hard drives. So in today's major software tools, normally what they do is to save all the necessary information into one giant big file, right? If we want to run 1 minute dynamic simulation, saving all the states, the file can be several gigabytes, right? Then what if we save different information to smaller files in pieces, right? By properly identifying the indices to where to correct the information, this can achieve some speed up. Right? Okay, any questions? And then the next project is applying the similar concept with GE Energy Consulting. So they do have their own commercial software tool called PSLF, Positive Sequence Load Flow Program. It can solve both power flow as well as dynamic simulation. And then one of the primary goal inside that project is to parallelize the PSLF software by applying PNL's parallel algorithm. Similar concept, and then they do see significant speed up inside their commercial software tools, right? Including the ordering algorithm for network solve. They see 15% improvement. And then factorization algorithm using the unidentified best solver, it is about 50 times faster than their previous in-house linear solver. And then regarding parallelization of the states, they achieve around 30% speed reduction. Right. And then the other improvements come from other matrices and manipulations. Let's look at the speed performance of this PSF tool with parallelization technique. This is tested on the full Eastern interconnection. This is about 3 times bigger than the WECC Western interconnection. Right? As you can see, 20-second simulation using 1 core, it takes around 400 seconds. This is much, much slower than the previous case because the size of the problem is much bigger. Using around 4 processors, you get around 2 times speed up. Right? And then this is the scalability curve. And then the more cores you use in this testing, you do not see much speed up. That's because of some internal implementation and also the parallelization math libraries being used in the Windows environment. And again, the simulation accuracy was not sacrificed. And this is the full models with every single detail being used by the power system operators and planners in Eastern interconnection. Right? And then next, I want to talk about one important application. Once we develop the faster computation techniques, how are we going to apply that? This is one of the examples and funded by the DOE WR.t. And then the main idea is to calculate the total transfer capability of today's transmission lines in real time. Right? As we know that the transmission congestion can be a big concern in today's power grid. It can easily cost more than $1 billion per ISO. ISO means independent system operator per year in the power grid. And then you have many, many ISOs in the US, right? So congestion is a big deal. And we want to develop the so-called non-wire solutions by using faster computation to move all the offline studies into online environment in order to enable the unused capacities of today's transmission wires. So if we look at today's NERC standard, in order to calculate the transfer limits of transmission lines, we really have to consider 3 types of limits. One is the thermal limit, the thermal capacity, right? And also voltage limit, as well as the stability limits. Now in this project, we want to develop a HPC-based algorithm speed tool, trying to speed up the computation. In today's practice, this is done in an offline mode. It is static. It is done seasonally. And once determined, this limit is used for the next 3 months. Right? And then in order to make sure everything is good, we have to assume very conservative, we call it the worst scenario. But in the real-time operation, majority of the time, your system is not stressed to that bad level. Right? So theoretically, you should be able to see an increased transmission capacity by using online computation. And then this is the computation process we developed in this WR.t project. So starting from base case, we want to search for the boundary of how we operate the system in order to maximize today's transmission capability. Right? Starting from the base case here, and then we search around one direction to find the first boundary point. And each of them represent one stressed operating condition. And then behind each of those the dots, we have to run contingency analysis, right, to make sure if you operate at this level, the system is fine when subject to different contingencies. Right. Then once we identify the first boundary points, we now developed a so-called non-iterative approach to search for the boundary points instead of search from the base case from scratch. This can save us a lot of time. This is the computational process. Once we have this point, right, we want to find the neighboring hood instead of starting from here and to do the binary search, step-by-step searching. This is very slow. This will save a lot of time. If you are interested, we have a nice paper just published in the Higgs conference. And then different contingencies can represent different contours, right? And then in order to make sure all the contingencies are okay, we need to find a minimum contour, which is highlighted in yellow. Right? Okay. Then this will be the end of the steady state-based approach. Next, we want to identify if these points can survive transient stability by running dynamic simulations. So each star here will trigger different type of dynamic simulations under different contingencies. Right? If something is wrong, for example here, we have to scale back the flow a little bit in order to make sure your transient stability is satisfied. Right? And once we identify this point, we will modify the contour a little bit. This will be the real-time, call it nomogram, the real-time limits to be sent to the system operators to operate the grid in the next 10 to 15 time frame. Right. Regarding parallelization, again, we can apply the distributed type of massive contingency analysis, right? Different cores for different contingencies. Also, for different contingencies, we can launch them simultaneously using multi-cores. And then for dynamic simulation, we want to have the two levels of detailed parallelization to gain speed up. And then we do have a GUI. So how many of you are familiar with Linux? Cool, very impressive. If I talk to power grade students, normally students do not learn Linux at all. Right? This raises some issues how we bring this parallel computing, because all the computation here on the left-hand side is done under Linux, right? But power engineers normally do not use Linux at all. Windows is the only operating system they use, right? Then later we want to fill this gap. Then we develop something called COS, trying to do the real-time display across different operating systems. So this is the dynamic computation process by launching multiprocessing, right? And then this is a tool we recently developed. This will keep monitoring one file representing the nomogram points just identified in the previous slide, right? Then once computation is done, then this will save all the information to a file. This tool will keep monitoring this file. Once this file is identified, this will be projecting all the information to a web browser-based GUI for system operators. So this will easily remove the gap for power grade engineers who do not use Linux. They don't have to, interact with Linux. Okay. So this is the real-time display. Whenever a computation is done, every 10 minutes, this will project to the web browser-based GUI. Okay? And then regarding computation time, in today's practice, to complete one case I just showed in the last slide, it will take several hours. Now, by enabling the parallel computing process, this can be done less than 10 minutes. For different real-time cases, the time can vary a little bit because some cases tend to take longer iterations to solve, right? But normally, it ranges between 250 to 370 or 400 seconds, which is below the 600 100 seconds, 10 minutes, right? Any questions for this application? Okay. So this is the second application, and this is about the high fidelity cascading failure analysis. We want to develop a tool trying to capture the dynamic process of cascading failures, right? Because the NERC is a North American Reliability Corporation who set the standards for the power industry, ISOs, to comply, right? They recently launched a new standard. So every single power company, ISOs, they need to run studies to investigate the impact of cascading failures under extreme events. In the previous standard, they are only required to run M-1 or part of M-2 contingencies. But now, extreme events are being considered, and you have to document what are the consequences of such a blackout. If you can remember, back in 1996, WECC had a system breakup event. Back in 2003, in August, there was a big North America blackout. Although such blackouts has a very low probability, but once it occurs, it can cause severe damages to our society. Right? We don't want that happen, but in today's practice, we do not have a set of good tools that can capture this process in order to do things like this. Right? Because for power grid planners who normally run studies, normally they don't have the protection system properly modeled in their big model. They just talk about for dynamics as well as steady state. There's not much tools they can use to fully understand the dynamic process of cascading failures, because it can take a couple seconds or it can take hours. It all varies. No blackouts follow the same sequence. Right? Then in this project, we call it DCAT, Dynamic Contingency Analysis Tool. We just finished. We partnered with ERCOT, with Siemens PDI, and APRI, and Southern Company, trying to develop such a tool. Then there are a few important objectives. We want to develop a hybrid simulation process that can switch automatically between dynamic and steady state simulations to mimic the cascading failure process, right? Once the system is subject to extreme event. Right? Then we want to model all the unmodeled pieces, especially the protection system, or special protection system, or RAS, remedial action scheme. These are the specifically designed for a particular condition. Once you lose a line, what are the control actions you should take? We need to have all that being modeled in order to generate a realistic system performance to better understand the process and prepare for future. Right? Then this is the simple flowchart we developed. Up here, we need to do some preparation, right? And then apply different stress patterns to create a bunch of scenarios, or you can use real-time cases to represent different operating conditions. Then we have a pre-screening process, because if you consider the full N-2, it will be millions of combinations if you consider all single outages for a big network. Pre-screening is a very important process to reduce the total number of runs we need. Right? Although we have the luxury to have the 23,000 core machines, but the total combination will be way bigger than that. Right? And we have this so-called cage process. This is the computation core of our cascading failure analysis process. I'm not sure if you can see this, but let me explain this. So we always start with a dynamic simulation, because under severe contingencies, say if you knock out a couple lines, a couple generators simultaneously, the traditional power flow can easily diverge, right? And then once you have a divergence, it might be caused by a true blackout, or it can be some numerical problems having the divergence. Now, solving a dynamic simulation will easily solve the problem. Right? Then on the left-hand side, we launch a dynamic simulation by properly modeling all the necessary and important pieces, including the traditional controllers of generators, exciters, governors, right, PSS, and also the protection relays for protecting generators, loads, and transmission lines. And also, we need to include other specifically designed SPS or RAS actions into the model in order to generate a good system performance. Right? Then once we run a dynamic simulation, we need to check if the system survives or not. If not, then this goes to the total blackout box here. This is a bad case. Under this set of initiating events, the system cannot survive. Right? It's that simple. What if I have a converged and stable performance, right? And then we have to check system behavior under the new steady state. If we have any violations, we want to capture those unmodeled process in dynamic simulation, right, into here, especially for those longer term actions like transformer tap ratio changing, like the overcurrent protection relays to chip lines. Normally they can take 30 minutes or even longer to do, but dynamic simulation typically takes 30 seconds or up to a minute to run. Right? Then there are a few pieces that we have to carefully design. One is about protection system models. Right? We want to leverage whatever being available to us in the PSLC software tool. This is the tool suite developed by the Siemens PTI team. Right? Then we want to protect generators against violations on voltages as well as frequencies. We need to comply with the NERC standard. The generator should have the rise-through capability. You should not really trip if the monitored voltage or frequency are within this range, right? So we have to properly model that inside our simulation process. And then regarding the load modeling, especially load shedding, we need to model the under frequency, under voltage load shedding relays in order to trip the load devices to protect them, right? Once your voltage or frequency is behaving weird. And then for transmission protection, we need to add distance relay protection, overcurrent relay protection, right? In order to make sure simulation is accurate. And then in order to check whether the system is entering to a new quasi-steady state, after each dynamic simulation, we need to check the speed deviation of all the synchronous generators, making sure they are running at same speed or similar enough speed, right? This is a flowchart we developed. The first dynamic simulation usually run up to 30 seconds. And then after each 30 seconds, we need to check it. If it's still not entering a steady state, we run another 5 seconds because it can be very lengthy to launch the dynamic simulation until system either goes to a new steady state or it exceeds the total number of iterations the users specified. Okay. And then another different but very important piece is to capture the post-dynamic simulation results by applying the corrective control actions that are only available in the steady state. Right? Then this is actually a zoom in of the big flowchart to the right-hand side. Once we have dynamic simulation, then we want to check if the steady state criteria is met by checking the voltage violation, right? If we want to chip any loads, if we want to enable any of those controllers for voltage correction, right? And if so, we have to, if any single tripping action happens, we have to go back to a new dynamic simulation. Right? Okay, so far we have implemented and automated this process in PSLC by developing the Python scripting. Then starting from new dynamic simulation, we can switch back and forth between dynamics and steady state. If steady state has something tripping, we go back to dynamic simulation again, right? And then, again, dynamic simulation can be very slow. And in PSLC, we have a nice Python script developed by Jose Canto at ERCOT. So it's a parallel version of PSLC, right? If we want to run 1,000 dynamic simulation using full ERCOT models in PSLC, using one core, it can take 1,200 minutes, right? But using 80 cores, this can be nailed down to 17 minutes. And we recently published a report here capturing all the details shown here. And then our tool will be made to public for download pretty soon. Any questions? Again, this is only a subset of our research portfolio. So if we look at the research agenda inside our electricity infrastructure group, we do have several other exciting areas like transmission resiliency. How do we improve system reliability? And by using the new PMU is phasor measurement unit, which is a faster and time synchronized measurement unit, trying to monitor the system states in real time. And then the HPC work we have been doing is under the grid analytics, this category. Also, we have the distribution system analysis and demand response. How do we control the load? How do we properly model the rooftop PV actions? And how do we better integrate the renewable energy into our grid, right? To make our grid cleaner, greener, and better. Also, renewable integration and energy storage. We do not only run system analysis, but we have also groups who are working on the material side, trying to develop an integrative materials for energy storage devices. Also, cybersecurity is one key area we have been working on for the past number of years. So, okay, one piece of information I want to share. We are actually hiring. So I will leave a couple flyers right here. So for students who will graduate soon or want to continue your research activities in Power Grid, PNL is a great platform for you to further explore your research activities. With that, thank you for your time, and happy finals.
Thanks. Any questions for Ruisheng?
Can you go back to around page 28?
28? Yes.
So here it says after 30 seconds, you only check the state of the system every 5 seconds. But essentially, all the information between time 30 and time 35 are lost because we didn't do any simulation between those time steps.
Actually,
no?
Go ahead. Partially correct. So we run the dynamic simulation for the first 30 seconds, and then we stop there and check violations. Violation means the standard deviation of speed deviation of other machines right at that point. But by checking this, we have to use a 2-second time window to check, right? So over this 2-second time window, we need to make sure all the generators will swing together, right, inside one big electrical island, making sure system is stabilized. If not, we have to run a new 5-second dynamic simulation, right, and then check right there at 35 seconds. But at that point, we need to go back by 2 seconds to check the speed deviation again, making sure if that is satisfy our specifications.
The next time you start the transient simulation at time 35, we do not have any information at the time step right before it. And how can we make sure the simulation starts from a reasonable initial state?
That's a great question. So the question is, how are we going to preserve information between time 30 seconds and 35 seconds, right? And in PSLC, there is a specific a command for you to stop and save that particular snapshot. So all the information, you don't have to go back to the initial state. You can save all the information right there. That will include the current state variables as well as their derivatives. So you will start right there by enabling that snapshot. and then start from there. It's just launching or marching further in the time.
But we do not have the simulation result at that time step. For example, 34.9, we do not have any transient simulation result.
We do.
You
so,
do?
Yeah, 30 seconds, I stop and check back. Means I will grab the information from 28 seconds to 30 seconds, check criteria, and then I need to run 5 seconds more, right? So now the time is at 35. All the information from t equals to 0 up to any time step, all the information will be saved into the channel file. So user needs to specify the channel file, which are the generators you want to monitor, make sure. So typically we can include all the synchronous generators there to check.
Other questions?
Yes.
Have you considered using GPUs for the simulation?
The question is, have we considered any GPUs for computation? For this research, no, because we have the luxury to use the big machine we have. It's basically a Linux clusters for the MPI type. And then for the OpenMP type, we do have another cluster sitting next to our room back then. But GPU is also affordable options to be used. So maybe in the future we can definitely explore that. But there are research activities being reported, in the papers and reports doing that. Yeah. But again, the computation algorithm should be similar enough.
I had a very basic question. This
Yes.
is obviously pretty far from my area, but I'm just curious. It seemed like there's a regulatory reason to do pre-computation of grid stability to try to figure out the maximum power that can be allowed to flow. Are there activities where very realistic simulations would be used for reacting in real time to a fault after it occurs?
So the question is, are today's offline computation be realistic enough to take control actions in real time when something happens, right? Okay. So actually, in today's practice, engineers tend to be very conservative because there were no tools available. There are no tools available right now trying to do the fast enough computation to prepare, arm, and act. Right? In the real time, say 5 to 15 time frame. Now there's no tools like that. So normally what they do is the margin is very big. So for example, the California to Oregon intertie, they have three 500 kV lines, and the thermal capacity is over 10,000 megawatt. But in real world, only less than that, 4,800 is being used as the max limit to be used. But we have run some studies, and it is possible if we were able to run fast enough computation by using real-time cases, then we can see like 700 megawatt increase of that capacity.
Sure, thanks. Yeah. Okay, if there are no other questions, let's thank our speaker, and everyone is free to come down and pick up a recruiting brochure for PNNL and also ask any detailed questions.
Thank you very much.